You know when you see a political poll and you just have to wonder, hold on a second, how in the world do they know what an entire country is thinking just by asking like 1,000 people? It honestly feels like some kind of magic trick, doesn't it? Well, today we're going to pull back that curtain and show you the powerful and surprisingly simple secret that makes it all possible.
So here's our game plan. We're going to start with that big puzzle, then we'll build up our statistical toolkit one piece at a time. We'll see how to describe data, how to compare it, and how to spot these hidden patterns. And then we'll uncover the one single idea, the big one, that ties it all together and finally solves the mystery. Are you ready? Let's dive in.
All right, Section 1, the 1,000-person puzzle. This is it, the central question that's going to drive everything else we talk about today.
Let's just put it right out there. How can this tiny little group of people act as a reliable mirror for a huge, messy, diverse population? It just feels wrong, totally counterintuitive. And yet, it works, and with spooky accuracy. The real question is, how?
I mean, just look at the numbers here. It's a huge difference in scale. We're talking about a sample that's a tiny, tiny fraction of a percent of the whole country. So to understand how we can make that giant leap, we first need to learn the basic language of statistics.
So let's start building that toolkit. Section 2, describing a crowd. See, before we can understand a whole nation from a tiny sample, we've got to get good at describing any single group of data first.
We've basically got three main tools to find what we call the center of a bunch of data. First, you've got the mean. That's the good old average we all learned in school. Then there's the median, which is the number that's literally in the dead center if you line all the numbers up. And finally, the mode, which is just the number that shows up the most often. So, which one is the best? Well, that really depends on the kind of crowd you're looking at.
To see what I mean, just picture a small company. You've got 6 employees making around 11 grand a year. But then you have the boss's son who's pulling in 200,000. This one single extreme number, what we call an outlier, is about to totally mess up our picture of the company.
And boom, look at what that one outlier does. The mean, the average salary, shoots up to almost $38,000. That's super misleading, right? Nobody except the boss's son makes anywhere near that. But the median, the middle salary, is just over $11,000. That gives us a much more honest picture, because it isn't so easily fooled by that one crazy high salary.
Okay, so besides finding the center, we also need a way to know how spread out everything is. And that's where this thing called standard deviation comes in. You can just think of it as a measure of consistency. Are all the numbers bunched up tightly around the average, or are they all over the map? This one number gives us the answer.
Okay, Section 3, the universal scorecard. So now we know how to describe a single group. But what happens when you want to compare two completely different things, like literally apples and oranges?
Let's try a classic example. A student gets an 83 in statistics. That looks like their best grade, right? But what if that was a super easy class and everyone got an A? And what if that 68 in policy was in a class that's famously difficult? The raw number itself doesn't really tell you the whole story.
And this is where that context is absolutely everything. Once you factor in the class average and how spread out the scores were, the entire picture just flips upside down. Turns out, their best performance was actually in policy. They were a half a standard deviation above the average. And that high score of 83 in statistics, well, they were actually below average for that class. Crazy, right?
The amazing tool that lets us do this is called the z-score. You can think of it as a universal translator for data. It takes every single number and reframes it, not by its raw value, but by how many standard deviations it is from its own group's average. And just like that, you can compare absolutely anything to anything else.
So now that we have these tools, we can start to spot these bigger, amazing patterns in the world. Which brings us to Section 4, nature's favorite pattern. Because it turns out, as you look at more and more data, a very particular shape starts to appear over and over and over again. So often, in fact, it kind of seems like it's a fundamental pattern of the universe itself.
And that shape is the normal distribution, but you probably know it as the bell curve. It's perfectly symmetrical, most of the values are clustered right there in the middle, and then it tapers off evenly on both sides. Things like people's height, blood pressure, even tiny measurement errors in a lab, they all follow this exact same shape. And the fact that it's so predictable is what makes it so incredibly powerful.
Yeah, because it's so predictable, we get this amazing statistical cheat code in any bell curve, no matter what it's measuring. About 68% of all the data will be within 1 standard deviation of the average. About 95% will be within 2, and nearly everything, 99.7%, will be within 3. This isn't just a coincidence. It's a core mathematical truth. You're going to want to remember this rule. It is absolutely crucial for what's coming next.
And that brings us to Section 5, the statistician's secret weapon. All right, we've got all our tools. We understand averages, we get spread, we get z-scores, and we know all about the bell curve. So now, it is time for the big reveal. The one single idea that connects everything and finally solves our polling puzzle.
So let's look at some real-world data. The number of times people on a particular island have gotten married. Now, as you can see, this is not a nice clean bell curve. It's all lopsided. Most people have been married 0 or 1 time, and then you have this long tail of a few people who've been married a whole bunch of times. So the population itself is definitely not normal.
But this is where the magic happens. What if we stop looking at the individuals? What if instead we started taking random samples, say 30 people at a time, and we calculate the average number of marriages for each sample, and then we plot those averages on a new chart?
And there it is. This is the secret. Even though our original population was all messy and skewed, the distribution of the sample averages creates a perfect, beautiful bell curve. It doesn't matter what the original data looked like. The averages of its samples will always form a normal distribution.
This absolutely mind-blowing phenomenon has a name, the central limit theorem, and it is, without a doubt, the bedrock of almost all modern statistics. It's the secret weapon that lets us make these incredibly precise guesses about a whole population that we can't see just by looking at the predictable behavior of its samples.
Which brings us right to our final section, from sample to society. Let's put all of these pieces together and solve that 1,000-person puzzle once and for all.
So, here's how the trick actually works. A pollster takes just one sample of 1,000 people. Because of the central limit theorem, they know with mathematical certainty that their sample's result is just 1 point on that predictable bell curve of all possible samples. And since they know the properties of that curve, remember our 68, 95, 99.7 rule, they know that 95% of all samples will land within a certain predictable distance of the real answer. And that predictable distance, well, that's the margin of error. It's not a guess, it's a calculation. And that's how they do it.
So in the end, statistics is this incredible framework for dealing with uncertainty. It's what allows a small, manageable snapshot to serve as a reliable stand-in for a huge, unknowable picture. And that leaves you with one last big thought. If this one statistical secret can so accurately reveal the opinion of an entire nation, just imagine what other profound truths are just sitting there, waiting to be discovered, in the massive sea of data that's all around us.